Okay, here we are with chemical quantities, and we are starting our lecture on the mole. And the mole is a measurement of matter, and we need to start this conversation by reminding ourselves what atomic mass and formula mass are. Since the actual mass of an atom is so small, it's 10 to the negative 23rd grams, atomic mass units are used to describe the mass of an atom or a compound. Now, you may recall from earlier in the year that we had a definition of carbon atoms, or a definition of the atomic mass unit, and it was 1/12 of one carbon-12 atom would be one atomic mass unit, or all of the other atomic masses are based on carbon-12 having 12 atomic mass units. And so the atomic mass of things is the mass of an atom expressed relative to the mass assigned to carbon-12, and its units in AMU. Well, from there we go to the formula mass, because then we need to start finding the mass of compounds. And the mass of compounds is the sum of the masses of all of the atoms in a compound or molecule. So you round your masses to no more than the nearest tenth. That means you don't get any closer to the whole number, but for multiple choice purposes, it's okay to just use whole numbers, because you're going to get an answer that's pretty darn close. So here we go with sulfuric acid. This is H2SO4, and here's how we find the formula mass for it. Here is H2, and so there's two H's in this. There's one sulfur and 4 oxygen. And so we're going to have H, the mass coming from the hydrogen, there's 2 times 1.0, is going to equal a total of 2. And then sulfur, which has a mass of 32.1. And then there's oxygen that has 4. There's 4 oxygen atoms in this molecule, and so there will be 4 times the 16, which is the mass of its oxygen. So let's take a look at the periodic table to remind ourselves where we find these. So here's our hydrogen over here with a 1.0 mass, and then here's oxygen with a 16.0, and sulfur is right below it with a 32.1. So if we're rounding to the tenths place, then it would be 16.0 and 32.0. Okay, then we can do the same thing with magnesium phosphate, and we want to examine this for a minute. Magnesium phosphate has these parentheses around it, and so what I'm going to suggest that you do is, instead of finding the mass of each atom, so you have 3 magnesiums and 2 phosphoruses and 8 oxygens, and you can do the math similar to the way we do it up here, I'm going to suggest you do it in a different way. And we're going to have, so what I'm going to suggest to you is, instead of calculating each one of these atoms individually and adding all their masses together, I'm going to suggest that you find the mass of the ion that's involved. So this is magnesium, and it's a metal, therefore this is an ionic compound. And over here, this PO4 is a phosphate, and what I'm going to tell you then is to find the mass of the whole phosphate ion, and then multiply that by 2, and then add it to magnesium. And this is going to come into play later on in the next couple chapters, where it's going to be easier to calculate masses that way. And so if we're going to do that, then we start erasing this, and we get 1 phosphate is going to be 31, 4 oxygens is going to be 64, 4 times 16 is 64, like over here. And if you add those together, it's going to be a PO4 equaling 95. Well, 2 95s then is 190. So let's see if I can draw that in here. That's going to be a 190. So we're going to keep the 72.9. So that'll be 72.9. And then we'll have 2 95s, 2 times 95 is going to equal 190. And I'm writing this without my mouse. I'm doing my trackpad for the drawing, so forgive my real messiness, although it's not much better than what you get in the classroom. And so those the 72.9 plus the 190 is going to wind up being 262.9, which is the same as what you get over here. It's just a different way of doing it, and it's going to be more efficient later on. Now this brings us to what is a mole. And mole is this new number that we have. Okay, so we have this mole, and it's this new number that we are developing. And just like there are a whole bunch of other numbers that are out there. So for this one, we call it the chemist's dozen. And the chemist's dozen it's used to express relationships between the number of atoms and the mass in a measurable quantity, grams. So we can start measuring things in grams and relate them to the number of atoms that we have. All right, now we use this so the mole is just another number, okay? So we have other words that mean numbers. A dozen means 12, and a gross is actually a dozen, so that's going to be 12 times 12, which is 144. There's a ream, and a ream is primarily used for paper, but I have heard it used for other things, and that would be 500. You may have heard of other ones. A score is 20, so if you've heard of 4 score and 7 years ago, our fathers brought forth on this continent a new nation from Lincoln's Gettysburg Address. He gave that speech in 1863. Well, in 1776, we brought forth this new nation, and the difference is 87 years. And so 4 score and 7 years ago was 87 years, and that winds up being that a score is 20. Then there's the mole, and a mole, just as dozen is 12, and a gross is 144, and a ream is 500. The mole is 6.02 times 10 to the 23rd. This is 602 sextillion. Okay, and so the 6.02 times 10 to the 23rd is actually 602 sextillion. It is a huge number. Okay, however, it is just a very large number, and it can be used to represent very large numbers of anything. It is a non-specific amount. Now, we tend to use it only for chemistry, but you can have a mole of anything. You can have, if you have a mole, 1 mole of anything equals 6.02 times 10 to the 23rd of those things. Okay, so a mole of sodium is going to be 6.02 times 10 to the 23rd atoms of sodium. A mole of water is going to be that many molecules of water. A mole of donuts is that many donuts, which happens to be the amount of donuts that you would need to feed the New York Police Department for a week. Then there's a mole of magnesium would be 2 times that number, which would be 1.2 times 10 to the 24th. Or if you look at it, it's 12.04 times 10 to the 23rd, and then you move the decimal for the scientific notation. Okay, if you have 3 moles of chlorine, Cl2, that's going to equal 3 times 6.02 times 10 to the 23rd, which equals 1.81 times 10 to the 24th molecules of Cl2. But then if we're looking at atoms, then there's actually 2 atoms for every molecule, and so that would be 6 atoms of chlorine for every 3 moles of chloride. I'm sorry. There would be 6 moles of chlorine for every 3 moles, 6 moles of chlorine atoms for every 3 moles of chlorine molecules, which would actually double that 1.81 to 3.61, because you multiply by the 602 times 6, and that's what you get. Of course, you didn't see anything of what I just said because I didn't scroll up, so I need to do this. And all of these are going to be 6.02 times 10 to the 23rd. And they are, because 1 mole of anything is this many of that number. So it's just like using a dozen. If I say, if you have a dozen donuts, how many do you have? 12. Okay, if you have a mole of them, you have 6.02 times 10 to the 23rd. Now this is a really big number that is used to count really small things. So keep that in mind, that if we're dealing with counting individual teeny tiny little things, then you're going to use a really big number to count really small things. Okay, and finally, you have 4 moles of magnesium phosphate, and that's going to have how many moles of atoms? So if we have 4 moles of magnesium phosphate, the number of total moles of atoms we're going to have is 4 times 3 to give us 12 moles of magnesium, and then 4 times 2 times 1 to give us our moles of phosphate, and then our 4 times 2 times 4 moles of oxygen to give us a total of 52 total moles of atoms if we have 4 moles of this whole magnesium phosphate. Then we could figure out the masses from there. Now that brings us to Avogadro's number, and this 6.02 times 10 to the 23rd is Avogadro's number. It is named after him, and here he is. This is Avogadro. He's a rather strange looking fellow. He's got that big old eye and the lump on his forehead. And I've always said that Avogadro should be Avogadro should be played in the biopic by Steve Buscemi, and that's this guy. And I know you've seen him before. He's been in Reservoir Dogs and Armageddon. You might recognize him, or Con Air. He's done a lot of he's a character actor. Right now he's on Boardwalk Empire on HBO. So anyways, this is the guy that should play that guy in the movie. But that's beside the point. Avogadro's number is this 6.02 times 10 to the 23rd, which is 1 mole. 1 mole of any substance contains Avogadro's number of particles, or that same number of particles. It is named in honor of Amadeo Avogadro, which, ironically, because we mentioned earlier when we were talking about score, lived for 4 score from 1776 on. Okay, he died 7 years before the Gettysburg Address, so he lived for 4 score of those 4 score and 7 years. Just sort of an odd coincidence there. Now, 1 mole of paper makes a stack of... Make 1 mole of paper, if you have this many sheets of paper, 1 mole of it makes a stack measuring beyond Pluto. I'm not sure it's over 6,700 light years, because that's a really long way. But it would be a huge stack. If every 500 sheets of paper is 1 ring. Okay, another astronomical term is that 1 mole of rice, if you had 6.02 times 10 to the 23rd rice grains, it would cover the Earth 250 feet deep. But 1 mole of water is 18 grams. And it's only 18 grams. And that's 18 milliliters, which is equal to about 2 tablespoons. That's all. That's really not a whole lot. That just means the water is really small, and molecules are very, very small. And so, that brings us to our molar mass. And the molar mass is the mass of 1 mole of particles in grams. Why has such a unique number been created? Well, here's why. 1 molecule of water has a mass of 18 atomic mass units. There's 2 hydrogens times 1.0, that equals 2.0. There's 1 oxygen at 16.0, that gives 16.0, and so you add those together and you get 18.0 atomic mass units. Now, 1 mole of water, so we go from 1 molecule of water to 1 mole of water. 1 mole of water is going to have a mass of 18.0 grams instead of 18.0 atomic mass units. So, molecule is to atomic mass unit as mole is to grams. And that is our molar mass of water. Molar being the adjective describing something that is of a mole. So the mass of a mole of water would be the molar mass, and that's 18 grams. If we have 2 moles of water, it would be 36.0 grams, which would be 2 times that 18. So Avogadro's number allows us to do 2 things. They're easy conversions from atomic mass numbers to grams, and easy conversions from numbers of particles to grams of particles. And that about does it for the notes portion of 10.1. There are some other things, some other practices that we need to take care of for 12.1. But for right now, your homework is, and so our homework for this is going to be page 296, number 9 through 15. And that is the homework for 10.1. And so that's it for this first section, and we'll see you guys next time.